So in this section, we consider sample data consisting of observed frequency counts arranged in a single row or column. This is a frequency table just like we talked about back in Chapter 2. We will use a hypothesis test for the claim that the observed frequency counts agree with some claimed distribution, so that there is a good fit of the observed data with the claimed distribution. A goodness of fit test is used to test the hypothesis that a frequency distribution for a population fits or conforms to some claimed distribution. The notation in this section looks like this. A capital O represents the observed frequency of an outcome or a category. Capital E represents the expected frequency of an outcome or a category. K represents the number of different categories or outcomes, and P represents the expected relative frequency or probability for a category. Finally, N represents the total number of trials. The requirements to do this type of test are: first, the data have been randomly selected. Second, the sample data consist of frequency counts for each of the different categories. And finally, for each category, the expected frequency is at least 5. So the expected frequency for a category is the frequency that would occur if the data actually have the distribution that's being claimed. There's no requirement that the observed frequency for each category must be at least 5, just the expected frequency. The test statistic for this type of hypothesis test looks like this. The important thing to notice over here is that we have a chi-squared, so we'll be using the chi-squared distribution. And this gets a little bit complicated because these i's here represent all of the different categories. So this is the observed frequency for category I, the expected frequency for category I, and again the expected frequency for category I. And the way we figure out those expected frequencies is we take n, which is the total number of trials, times the probability or the relative frequency for that category for each one. Okay, to do our hypothesis test, first let's talk about step 1. Again, this is where we come up with our claim and with our null and alternative hypotheses. So first we want to write down the claim or the statement being made in a complete sentence. Now for a goodness of fit test, we're going to write the claim so that it says that a frequency distribution for a population does not fit the claimed distribution. Now to write our null and alternative hypotheses, this is pretty easy because these are always going to be basically the same. The null hypothesis will always be that the frequency distribution for the population does fit the claimed distribution. The claimed distribution should be specified here with numbers. The alternative hypothesis will always be that the frequency distribution for the population does not fit the claimed distribution. So in other words, that it's different than the distribution being claimed. Here's an example. A sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their grandchildren is different today than it was in 2000. According to the Census Bureau, in 2000, 22.8% of grandparents have been responsible for their grandchildren less than a year, 23.9% have been responsible for 1 or 2 years, 17.6% have been responsible for 3 or 4 years, and 35.7% of the grandparents have been responsible for their grandchildren for 5 or more years. So this is our claimed distribution, these proportions or percentages that are given here. So the way we're going to write the claim is that the distribution for the number of years caregiving grandparents are responsible for their grandchildren is different today than it was in 2000. In other words, different than these percentages that are given that came from the Census Bureau. So our null hypothesis is that the distribution is the same as the information from 2000. So here we are just putting the values in a table to make it more clear. So we have the number of years responsible, and then for each one we have the percentage that we were given up here just turned into a decimal form. So that's the claimed distribution. Our alternative hypothesis is that the distribution is different than this one that's given in the null hypothesis. Now, the next place that this is a little bit different is in step 3, where we're calculating the test statistic. And remember, we looked at the formula a couple slides back. It's very complicated, and especially if you have quite a few categories, calculating this by hand can be a very lengthy process. So we're going to talk about how to do this using technology. Now, in order to do this with StatCrunch, you still have to calculate the expected frequency for each category, but that's really not very hard, because all this is the number of trials, which is n, times the proportion p from the claim distribution. So you just do this for each one of the different categories. The observed frequencies that we had in the formula for the test statistic, they actually come from the sample data. So you should already have those numbers. Let's look at an example. In our example about caregiving grandparents, the sociologist conducting the study randomly selected 1,000 caregiving grandparents and obtained the following data. So here again we have the information in a table, how many years they were responsible for their grandchildren, and then the number of grandparents out of the 1,000 in the sample that fit into that category. So these values will be our observed frequencies. Observed frequencies always come from the sample data. Now, to get our expected frequencies, we need to look at the claim distribution that we stated in our null hypothesis, which was this. So we have the number of years responsible and then the proportions that we had. So we're going to use these proportions to find the expected frequencies just by multiplying each one of these by our sample size, or our number of trials, which is 1,000. So when we do that, we get, for the less than 1 year category, we get 228. For 1 or 2 years, we get 239. For 3 or 4, we get 176. And for 5 or more, we get 357. Now what we're going to do is look at how we would put this into StatCrunch and what we would do to find our test statistic using StatCrunch so that we don't have to calculate it by hand. So here's what we would do in StatCrunch. You at least have to put in the observed column and the expected column. So these again are the frequencies. This observed is from the sample data, and the expected is what we just calculated by multiplying those proportions times the number of trials. So there are the two columns you need. In this one, I put over here the years responsible in another column just so that I could keep it straight. But that part you don't actually have to do in StatCrunch. Okay, then to run this test in StatCrunch, you do stat, go all the way down here to goodness of fit, and we're doing a chi-square test. Here's the window that you get. You tell it what column your observed frequencies are in and what column your expected frequencies are in. The only time that you don't have to do the expected frequencies is if each of your proportions for each of the categories, if they're all equal, and then it will calculate them for you. But in this one, we had different proportions for the different categories. And we want it to just display the expected frequencies for each one. Okay, and here's what we would get from StatCrunch. So this again tells us what columns our observed and expected frequencies are in. This, where it says chi-square, is our test statistic. And notice here it gives us the number of trials, or the sample size n, tells us the degrees of freedom, which is 1 less than the number of categories. It calculates our test statistic for us, and it even calculates our p-value. And down here it reminds us of what we had for our observed and expected frequencies. Okay, so step 4 is finding the p-value, and you do also get this from StatCrunch, but this would apply if you wanted to check what you've gotten in StatCrunch, and it's also helpful to know what it is that you're actually doing to get the p-value. So the most important thing here is that a goodness of fit test is always going to be a right-tailed test. We can't really tell that from looking at the alternative hypothesis, but this is always a right-tailed test. We use the chi-square distribution, and we use k-1 degrees of freedom, where k is the number of categories. So if we wanted to calculate the p-value with your calculator, you would take your test statistic that you found and put it into the chi-squared CDF function. So you do chi-squared CDF. Since this is a right-tailed test, we're starting with the test statistic, going up to a big positive number, and then putting in our degrees of freedom, which is k-1. Now, if you're already using StatCrunch to find the test statistic, it will also calculate the p-value for you. Here's an example. Here's the result we had before from StatCrunch. So we found our test statistic for this one was 6.605 approximately. If we want to check this p-value that StatCrunch gave us, we would, on our calculator, we would do chi-squared CDF of 6.605, put in a big positive number, and 3 because we have 4 categories here. So the degrees of freedom is 1 less than that. Okay, the last thing we need to talk about here is writing the final conclusion. This is a little bit confusing because remember that our null hypothesis is that the frequency distribution for the population does fit the claimed distribution. So if our initial conclusion is to reject the null hypothesis, then our final conclusion is that there is sufficient evidence to conclude that the distribution is different than the claimed one. Now, another way we can say this is that the distribution for the population does not fit the claimed distribution. Remember, in this case, the claimed distribution was the null hypothesis. So if we're rejecting the null hypothesis, we're saying that the population doesn't actually fit that distribution we had in the null hypothesis. Now, if our initial conclusion is to not reject the null hypothesis, then there's not sufficient evidence to conclude that the distribution is different than the claimed one. This is another way of saying that the distribution for the population does fit the claimed distribution.